All right, so we're going to build off what we know about the gravitational force to talk about the gravitational field. So this introduction's really going to focus more sort of on the gravitational field as a concept, and we'll spend plenty of time in class tomorrow dealing with sort of how we calculate the gravitational field. But let's start with, again, with the universal law of gravitation. So magnitude of the gravitational force is given by G, big G times the product of masses divided by the distance separating the masses squared. And so one of the things that we want to emphasize is that this tells us that gravitational forces are in action between two masses. And all we're going to do is start by actually relabeling those masses. So instead of calling one m1 and the other m2, and the distance between them r1, 2, we're actually going to relabel them. So one we're going to call the test mass, the other one we're going to call the source mass, and then r is just going to be the distance between where the source mass lies and where you place the test mass. So we're going to sort of relabel our two masses, and we'll see why in a second. So sort of fundamentally what this means is I've got some source mass sitting out there, and what I want to do is I want to probe what's going on around that source mass by bringing up some second test mass. And so here I'll have my test mass, I'll place it in the vicinity of my source mass, and I know that when that happens, what I'm going to have is I'm going to have a gravitational force that the test mass will feel. It's going to lie along the line connecting them. It's going to care about both how big the source mass is, how big the test mass is, and the distance separating them. And so in this case, I'm going to get something like this. It's going to be attractive. Well, if I bring up a second test mass, put it in a different place. So again, in terms of just probing this field, or maybe I move this test mass over, is probably a better way to think about it. So if I take my test mass and move it over, what I'm going to end up with then is, well, there's going to be some new line that I know my force will lie along, that the test mass will feel. It's still going to care about how big is the source mass, how big is the test mass, and the distance separating them. And because now my test mass is a lot closer, and in fact it's about half as close, it'll be roughly four times larger than what that force was initially. So I'm going to have some relatively large force, gravitational force, that my test mass feels at this point. And so the idea here is what we're saying, well, so there are three things that this force sort of cares about. How big my source mass is, how big my test mass is, and how far away my test mass is from the source mass. And I only want something that really cares about the source mass. So I know that one way that I could get, let's say this force happens to be 4 times as large as this one. Well, I could get this one, the force over here, to be equal to this one simply by making my test mass 4 times bigger. That would give me the same force. But I don't want something that depends on what test mass I use. I want something that really only cares about the source mass and how far away I am from the source mass. So what we're going to do is we're going to define a quantity called the gravitational field. And so little g is going to end up being the gravitational field. And you notice that what we do is we get little g by taking the gravitational force and dividing out the impact of the test mass. So you'll notice if I rearrange this, this looks pretty familiar, right? The gravitational force is some mass times the gravitational field. And so why does this make sense? Why does this seem so familiar in talking about this concept of the gravitational field? Well, so let's go back to something from the very beginning of 298. So let's say I drop two objects with different masses near the surface of the Earth. So here's mass 1, and it's clearly bigger than mass 2. And I drop them, and I know that there's going to be a larger gravitational force on mass 1 than there is on mass 2, because I get this by saying, oh, this is just mass times little g, mass times little g, and little g near the surface of the Earth is 9.8 meters per second squared. So if mass 1 is bigger, it's going to have a larger weight, it's going to feel a larger gravitational force. But when I think about the gravitational acceleration, The gravitational acceleration didn't care about the mass that I was dropping. Right? You drop some large ball or some small ball, and they're both going to fall with a gravitational acceleration equal to 9.8 meters per second squared. And the reason this makes sense, so sort of why is the acceleration of both objects the same? The reason this makes sense is because what up until now we've referred to as the gravitational acceleration, what it actually is measuring is the gravitational field, which only depends on the source mass, which in this case is the Earth, and how far away you are from the Earth, which we happen to be near the surface, so we're basically one Earth radius away. So we've actually in some sense, we've dealt with the gravitational field since we first started talking about gravity. We just didn't think of it in terms of the gravitational field, but that's what it was. So when we look at this equation, and we said, hey, the gravitational force is an interaction between two masses. One of them is explicitly written here. That's the test mass. That's whatever you're dropping within the gravitational field. But the gravitational field itself depends on the source mass, in this case the Earth. So our interaction between two masses is still there. It's just that one mass we're writing explicitly, and the other mass is the mass that's causing the gravitational field. So it's buried inside G, if you will. So what we're going to do is we're going to say, well, we can play exactly the same game that we did before. But instead of putting some test mass out here, all we're going to do is say, well, what's going on at point P is going to be asking about the gravitational field. And so there's going to be a line that connects my source mass to point P. In this case, the gravitational field at point P is going to point towards the source mass because gravitational fields always point towards their source mass. And if I move to a different point, say here P prime, again I've got a new line that connects P prime to my source mass, and now I'm closer, so I haven't changed what my source mass is, but because I'm closer, the gravitational field is going to be much stronger. And again, if I look at this and say, well, I'm roughly half the distance away at point P prime than I was at point P, then the gravitational field at P prime is probably going to be about 4 times stronger than what it is at point P. And so you notice that in both cases the gravitational field points back towards my source mass, and it points and then it cares about how big the source mass is and how far away you are. Right? So the way that we're going to calculate the gravitational field due to a point mass is going to be given by this expression. And the big difference between this expression and our universal law of gravitation is the universal law of gravitation was a force, and so it cared about two masses. The gravitational field only cares about one. It cares about what the source mass is, not the test mass that you might put at point P to feel some force. So here m is the mass, that's our source mass creating the field. R is the distance from the center of the source mass to the point where you want to know the field. And then r hat is the unit vector that again lies along the line connecting the point mass, connecting the source mass, and it points towards the source mass. So it always points back towards the source mass here, r hat does. Well, again, if we want to turn this into a force, all this says is, well, go place your test mass here at point P, and then it'll feel a gravitational force. And so what you notice is, if you think about this as a vector statement, since mass is always positive, part of what this tells us is the gravitational field is always going to point in the same direction as the gravitational force. So put any mass here at point P, it's going to be attracted to the source mass. That tells us that the gravitational force is going to point towards the source mass. since mass is positive, the gravitational field must point in the same direction. So this is why we know that r hat, in the way that we're defining r hat in this particular equation, is always going to point towards our source mass. So if we think about sort of the previous video that you guys watched, it was talking about calculating the magnitude of the local gravitational acceleration. Well, really, we can use that exact same expression to talk about calculating the magnitude of the local gravitational field, where m, instead of being the mass causing the acceleration, is now the source mass creating the field. It means the same thing. The source mass is what causes the acceleration that you feel. R is now the distance from the center of your source mass to the point where you want to know the field. So instead of being the distance from the center of your mass to where you want to know the acceleration, it's exactly the same thing to say, well, the distance from the center of the source mass to the point where you want to know the field. And so if we want to talk about the local gravitational field, say, on the surface of the Earth, that's going to be given by the same expression that we saw for calculating gravitational acceleration on the surface of the Earth. Big G times the mass of the Earth over the radius of the Earth squared. If you want to know about at a height h above the surface of the Earth, then again, you haven't changed the source mass. That's still the Earth. G is always constant. What you have changed is how far away you are in the field. And so now we've added this extra distance h to the denominator term. If you want to know about the surface of the moon, well, now you have changed the source mass creating the field. So the local gravitational field around the moon cares about the mass of the moon. And then again, if you're on the surface of the moon, then you want to know how far away you are from the moon's center. That again is going to be the radius of the moon. So there is no difference in terms of talking about the gravitational acceleration and the gravitational field. They are equivalent.